All right, folks, it's the summary here. I think we're getting to the summary here. Do I have? No, I have one more page. No, I already did that page. What am I doing? Discard that. All right, here we go. Our last few things. All right, so this is all falling under in your outline. If you know where we're at right now, and we doesn't seem like we've gotten very far. So we've talked about the intro to metabolism, a lot of terms there, energy in general, the laws, the terms, the laws themselves. We talked about the Gibbs free energy equation. So we have our last two things to do, which is talk about equilibrium again and metabolism again. So we're going to take this Gibbs free energy and now apply it to like metabolism. Okay. All right. So here we go. So we're all the way down at the bottom here, and we're talking about equilibrium. Well, we already mentioned equilibrium is definitely going to be a total delta G of 0. Okay. That's what this is saying right here. Okay. We know that. But we mentioned before that reactions have a tendency to move towards maximum stability. Well, all reactions will want to reach this maximum stability. All reactions will want to reach this, okay? They will want to reach 0. They will want to be at equilibrium. But will they get there? Well, that's an interesting thing, and we're going to see a very important statement made down here. So that's like what equilibrium is. It's having a delta G of 0. So just get that in your head right now. Letter C, metabolism and energy. Here's where it all comes together. Okay. First off, we want to mention the difference between exergonic and endergonic, which we already mentioned. Exergonic is like exothermic. Okay, it has a negative delta G, and this is where energy goes out. Energy out, and it loses its free energy. Loses energy out. Loses free energy. Okay. So it's not going to have as much. Like once it releases that energy, like that match, once it releases energy, it's like it's all puffed out as a negative delta G. That's why it was able to release that energy. Okay. And chemical reactions are either going to be exergonic or endergonic. Okay. And now for the endergonic. Endergonic, delta G. So if this one energy was out, this is energy in. Energy in. So this is going to be costly, these guys. You're going to spend energy on them, right? Okay. And if the energy is going in, then it's going to absorb and it's going to increase free energy. So that's why it's positive. Okay. Increases free energy. All right. Now, very, very important statement here. Metabolism. We talked about metabolism. That's all the reactions going on inside an organism. Never reaches equilibrium, or else that living thing is dead. So we're always trying to achieve this equilibrium, this homeostasis, but we never get there until we're dead. Okay. That sounds like, whoa, deep, like the ultimate goal is to die. No, the ultimate goal is to try and get to that equilibrium, that homeostasis. But we must take in energy and we must release energy to keep us maintaining that. That's why we have these feedback mechanisms that we talked about in the last unit and all. We have to keep that going. So energy in, whoop, we are always taking energy in, goes to our cells ultimately, waste got to come out. Okay, and that's how we keep our balance. That's how we maintain our homeostasis. If energy goes in, then something's got to come out. There's got to be a payoff. Okay, and finally, this little thing here, an isolated system can reach equilibrium. That's that thermos of mine again. So it was an isolated system. It can reach equilibrium. And so an isolated one can reach an equilibrium, but then no more work can be done. So take that hot soup again. When the thermos cap was still on it, it was actually at equilibrium. It wasn't given off heat. Like I could hold the thermos and I wasn't getting hot from it, and it wasn't taking in heat from the outside. Nothing was going on. It was at equilibrium. But as soon as I opened that up, then it started to be able to release that energy and it became an open system. But an isolated system can reach equilibrium, but then it can't do any more work. So that thermos, while that soup was in there, that soup couldn't affect anybody. Okay. And living things are not isolated. Remember, we are open books. We are open systems. We are releasing energy. We're taking in energy. All right, so that sums it up. And so the next thing we're going to be doing is we're actually going to do plug and chug with the Gibbs free energy equation. If I can find my worksheet here. Okay, so this is going to be your worksheet here that you're going to be doing. And here's nicely the Gibbs free energy equation at the top. Okay, and this is plug and chug. Okay, and the beautiful thing about that is the temperature is in degrees Kelvin, so no adding 273. But it asks you a few questions. It just says, how do we relate this equation? What I like about this chart is, what do you notice about this column here? That's that delta H, which stands for enthalpy. Remember, that enthalpy is increasing. What's happened to temperature? Temperature is remaining constant. And delta S, which was entropy, that's remaining constant. So we're basically saying, what's going to happen to delta G if we keep entropy and temperature constant and we only change the enthalpy? Okay, so you're going to plug and chug here. You're going to plug these numbers into this formula and solve for delta G. And then you're going to answer some questions on the next page of this about what happened to delta G when the delta H increased. Why? What happens to delta G when delta H would decrease? Why? Okay, then the next chart, you're going to see entropy stays constant, but this time we're going to increase temperature and we're going to keep enthalpy constant. So what we're doing is we're trying to relate, because I know you've taken math classes, but there's math fearers out there that hate like math things. And what we're looking at is we're looking at this equation. We're saying delta G. What's going to happen if this increases to delta G? Well, that's a direct relationship, delta H and delta G. So if H increases, enthalpy increases, so will delta G. But what happens if either one of these increase? Because there's a minus sign here. If this increases or this increases, it's going to cause delta G to decrease because you're subtracting it from that. So it's just another way of like plugging and chugging and doing this. And it's easy points to just do this and answer a few of these questions. Okay, so do that, and that's it for this first part of our energy unit. It did take a few things here, videos here, but hopefully I kept you entertained with my thermos story, definitely. All right, take care. Bye.